Okay, hello everybody. Welcome to thermodynamics lecture number 32. I have special guests with me today. I have my daughter Ava and my son Eli here today to wish you guys good luck on your exam. So, what do you say, guys?
Good luck on your exam.
Okay, great. See, now that you have some cheering section. Okay, bye guys. Bye. Okay, so yeah, they've been hearing all about thermodynamics from me as I've been talking about it and giving my lecture and here at home. So I thought maybe I'd get them involved. Okay, maybe you'll see my wife sometime and my dog. I don't know. Maybe they come into the future lectures. All right. So today, what are you doing today? All right. So tomorrow, big day. We have the exam tomorrow. I'm giving this lecture. It's actually 2 days. Today's Tuesday for me, but for tomorrow, when you see this lecture on Wednesday, you'll have the exam the next day. So I think the main point of the exam is that I'm going to be assigning it on Canvas, and I'll send out a notification just in case you don't see it. You'll have the 50 minutes to do it, plus an extra 10 minutes to submit the exam on Canvas. As you would like a homework assignment. So it should come natural to you. You guys have been doing the homework assignments and submitting them. I know sometimes it's tricky and it doesn't work, but please, just make sure you hit submit and don't run into the same troubles you run into sometimes with the exams. So that we can get them in there and everybody can get graded. Okay. So the exam, what is it going to cover? So I've had this question from a few people. The exam is going to cover pretty much everything we've done up until about a day ago. I don't know if we're going to cover a lecture ago. I don't know if we're going to cover what's in today's lecture. I'll say we're not going to cover what's in today's lecture. We're going to cover entropy and change in entropy, but we're not going to cover maybe the relation that I'm using today for the exam. So, but still, I mean, it's good to know. We're gonna review. It's good to watch this lecture because I'm going to be giving you some tips that will be really helpful for the exam. So don't tune out. Okay. Certainly pay attention to what I'm doing. I'm just probably not going to cover everything that is in this lecture on the exam. All right, but what was on last lecture? So last lecture we talked about the entropy balance for a control volume. And I asked, now I'm asking here, which term is not in the entropy balance equation for a control volume? What's not in the entropy balance equation for a control volume is the mass flow rate times the inlet enthalpy minus the exit enthalpy. That's in the first law equation, right? M dot He minus Hi, okay? So this is everything else is in there, right? The rate of entropy reduction, that's a sigma. The change in entropy of the control volume, that's ds dt. The mass flow times the specific entropy minus the outlet specific entropy, that's in there, and the heat flow divided by the temperature with which the temperature was transferred across the boundary, or the heat was transferred across the boundary. Okay, those are all in there. And most of you got this right. I got 59 respondents, which is great. That means only a couple people didn't take the quiz or the survey. So good. Still, responses are pretty good, and people are still engaged here. Yeah, 2, 2, 4, 2. So I don't know. Some people just maybe throw some answers in, but if you did get it wrong, you should check your answers and make sure you're understanding the material. Okay, as I said, exam is open book, so you can use any resources you want. It's not going to be particularly easy, and it's not going to be particularly, at least that's what I think. I don't know, you guys are really smart, so I don't know, maybe you just do really well anyhow, but it's definitely something that you may not finish. So if you don't finish the exam, don't freak out, don't worry about it. It'll be fine. The exam, one more thing to mention about it, it probably will be the same. I'll probably have some multiple choice or short answer questions in the beginning, like I usually do, kind of warm up questions, and then I'll have some problems. So the warm up questions will be similar to what you see in the survey, right? I don't know. I'll come up with some questions that you will answer, and put them in as short answer questions, which are actually quite good for your points, right? So if you get those right, then you can boost up your score. Okay, all right. Let's continue on to what we're doing today. Today I'm going to cover a lot of slides because a lot of the stuff we've kind of already done before, and it's not adding very much to the material. But it'll be good review. Some of it will be a review of what we've done and how to solve problems, and some of it will be kind of not even necessary for us to go through. For your exam at least, it'll be useful for future reference. So the property data. So last time we actually did stuff like that. We did the control volume, the entropy rate balance for control volume. That's as far as we're going to go for the exam. But if we wanted to calculating entropy change a little bit more in different ways, right? The property data that we have in the tables can yield relationships among properties that are established using what are called the TDS relations. Now, I'm not deriving the TDS relations. I may do that in a separate lecture or something, but the TDS relations are actually quite important. They're a combination of the entropy balance and the first law balance, okay? It's like if you take the first law energy balance is where you get the du and the dh here, and you put it together in the PDV term, which is like a work term, you put it together with the entropy balance, which is where the TDS comes from, you end up getting this equation. Now these are pretty useful sometimes for solving solving problems. We may go through some more problems like this on Friday using the TDS relations. So I wouldn't worry about it right now, but definitely something you want to consider. Another thing you have to consider is if you look at this TDS equation, so TDS equation for the H version, so TDS equals dH minus VdP for a process that goes across the vapor dome. So for example, a process that might go from F to G. So you end up getting, since a constant pressure process across the vapor dome at a constant temperature, you end up getting ds equals dH over T. And because the temperature is also constant during the phase change, we get SFG essentially. We don't have to integrate. You can just take the difference. So you have SG minus SF equals HG minus HF over T. So the relationship is applied in the property tables for tabulating SG minus SF from known values. And so this is actually what they use in the property tables to calculate those. So that's kind of an interesting relation. That's not something you probably use very much, but it's also something it's kind of probably gets to have in your back pocket. It's a result of the TDS equations. So remember I said that thermodynamics is only really, excuse me, two equations. Well, this is the TDS equations are like taking those two equations and putting them together. Okay, that's what you're doing. It's nothing new really. It's just kind of mixing and matching those things. Okay, so here's an example where they do this, and I'm not going to belabor this, but consider water vapor at 100 degrees C. So a lot of these slides come from the textbook provide these slides, so I use them because I think they're useful and they line up really well with the book. But I don't know. So sometimes I don't know exactly what's going on here, but in this case, you can calculate the change in entropy across the vapor dome from the saturated gas to the saturated liquid. Saturated vapor to saturated liquid using the TDS equation. So here you go. You can find SG minus SF using the HFG value from the table. Or you can just look at it at the table. So that's why this is like silly, because you can just look at the table and find SFG. Why would you calculate it and risk calculator error? I would always look it up. Okay. Oh, I'm moving myself. All right. So let's go here. The other thing that we have to do is consider entropy change for an incompressible substance. Incompressible substances are things like liquid, water, right? It doesn't compress. Gases compress, so gases are a compressible substance. So the incompressible substance model assumes the specific volume is constant and the specific internal energies depends on temperature, U equals U of T, just like it does for an ideal gas. Thus, du equals C as a function of T dt, where C denotes the specific heat. Right, so we use specific heat for liquids as well, as you recall. With these relations, the TDS gives us something like the following, where and we just kind of follow it. ds equals dH over T, and here you have S2 minus S1 equals C, the natural log of S2 minus S1, in which case you have you don't have any pressure term. Incompressible means that it's independent of pressure. Okay, so then here you can see that for a liquid or for incompressible substance, the entropy change or the entropy is only a function of temperature. Only for liquids, not for gases, okay? I know, confusing, I know. But because the pressure drops out, you don't have a PDV term, you don't have any compressibility, you end up losing the dV term in the TDS equation, and you end up getting with S2 minus S1 equals the specific heat times the natural log of T2 over T1. All right. So, or as I say, you look it up in the table. Okay, so here's where we got our pressure correction term. You know how we did this S naught thing? So the TDS equations are what gave us that pressure correction term. Remember the pressure correction term we've been dealing with and talking about for ideal gas? Well, it happens to come from the TDS equation. All right, so here's two versions, right? So there's two actual versions. There's the version that uses du over pdv, and there's the version that uses ds vdp, dh and vdp, right? So if you assume ideal gas with constant specific heats, you have CV as a function of temperature. Actually, not constant specific heats in this case. They're integrating, so they're assuming CV is now still varying with temperature. You get the following relations. We've been using the one on the bottom right. This S of T minus S of T, T and P is equal to the change here. This is the Q over T term, and this right here is the pressure, what we call the pressure correction term. Okay, so the pressure correction term is something that we have been using. Now, if I get down to this, we know, and I've already told you that this S naught as a function of T has been already tabulated. So now you know, if you look at the slide, you know where S naught of T actually comes from. S naught of T comes from the change from temperature to some reference temperature from Cp to T dt, where T is some arbitrary reference temperature, usually taken as 0. Okay, so now you know where this comes from, right? So this S naught of T is actually some sort of reference temperature, or S naught of T is this value that you can look up as a function of temperature, which you can use then in the TDS equation to get what you need, right? And so there is our relation that we've been using, this one right here. Essentially, we know that the change in entropy is equal to S naught of T minus S naught of T at the other temperature minus R natural log of P2 over P1. So that's the equation we've been using already for an ideal gas. That's why I say it's a little bit of review. And here, right here, we've already done this one in homework too, where we use the molar specific version of this, where S bar, delta S bar, essentially, we use S bar naught. And you can see the tables. In the tables, you can find these values for different gases, A22, A23, A24, etc., and find these. Okay, so this is where you're finding these change in entropy values that we've been calculating, and now you know where it comes from. Okay, all right, it comes from the TDS equations. So the TDS equations are kind of important. We use them, but we don't really think about them very much. We just sort of use them for finding things. Okay, here we go. The change in we've already done something like this, so you can look at this yourself. Essentially, we get S naught 1 and S naught 2, from the tables, which we've done before, and calculate this. So you can go through these yourself, and you can do some practice problems. I suggest that before the exam. Okay, so let's think. Calculating entropy change of an ideal gas, tables A22. These are reference pressure and volume. All right, we're skipping this one. We're skipping 44. So I'm just going to put in here, we're skipping these guys because we don't need to pay attention to that right now. The other thing we can do is if we have constant specific heats, we can pull the specific heat value out of the TDS equations, out of the integral, right? Like they're doing here and here, right? You're pulling them out of the integral, and essentially now you have for an ideal gas with constant specific heats, you've got a very simple equation to solve. CV ln T2 over T1 plus R ln V2 over V1, or the other way around. Okay, here's something that's just really important to know. These two equations can be used interchangeably. There's not a specific situation when you need to use one or the other. They're equivalent to each other. You just have to know which thing you have in your problem in order to solve. For example, if you have a problem that has changing volume, you'd use the left one. If you have a problem that has changing pressure, you'd use the right one, right? And so this is the most important thing. So in this case, this one right here on the left, the CV, this would be if you have like a piston cylinder thing. You have V2 over V1. And the right one would be, say, if you had a constant pressure process that would use you'd have the changing pressure. But it doesn't matter. You can use them interchangeably. They don't they're based on thermodynamic properties. They don't apply to specific things. The only thing that they apply to that you need to make sure that you understand, and that is that these equations are only to be used for ideal gases with constant specific heat. Okay, don't start using these for steam. I'm gonna freak out, so don't do that. Okay, these are for ideal gases assuming constant specific heat. So if you do that, these are fair game. Like if you have a problem that says you assume constant specific heats, and you want to know what the change in entropy is, you can just go have at these equations and use them. Okay, so that's totally fine. But just make sure your assumptions are correct and that you're able to make those assumptions for the problem. That's the most important part. Really, in thermodynamics, that's what it's all about. Using the assumptions that are appropriate for the problem that you're solving. You know, if you're solving a saturated steam problem and you start using the ideal gas law, right? Can't do that. If you start have an ideal gas problem and you start using the steam tables, that's not good, right? Not good. There's no quality in ideal gas. It doesn't exist, right? No such thing. So make sure you know the kind of liquid or fluid you're talking about before you start solving problems. Okay. All right, so there's some helpful relations that you could use. Now, if we go here, we can derive a couple of really important relations. And I'm going to use these in a couple of examples for us. Well, use them in one example. And they go kind of like this. So let me move here. So in the case of what we call an isentropic process, oops, what is this? Change in ideal gas assuming constant specific heat. I'm going to say, I'm modifying the slides right now. I'll repost these. An isentropic process has S1 equals S2 and, oops, what happened? Okay, and isentropic has S1 equals S2 and it has adiabatic, Q equals 0. Right, adiabatic. Okay, that's the definition of an isentropic process. Let's just do that like that, okay? Good, isentropic process defined. All right, so now we've talked about this before. We've talked about adiabatic before, and we've talked about, I'll move myself back up here. Okay, so we've talked about adiabatic before. That's where Q equals 0 for a process. For a process where S2 equals S1, that's called a reversible process, right? It's one where S2 equals S1 and the sigma, excuse me, is 0, right? And there's no heat transfer. That means that term of the equation goes away. And then what you're ending up with are the TDS equations that look like these. 0 equals, and for constant specific heats, if we want to assume that, constant specific heat, again, we have, for an ideal gas, we have the same relations that I just discussed earlier. And then what happens is you can use these relations, Cp of a function of t equals Kr over K minus 1. When they do this, by the way, this doesn't mean Cp times T. This means Cp at that temperature, okay? Be careful. That's not Cp times T. All right, so it's Kr over K minus 1, which I've given you these relations before. Cv equals R over K minus 1, and Cp equals Kr over K minus 1. These are relations that we should have learned in Chapter 3, but I did a bad job, and I kind of forgot to go through all those. And so I kind of did a little bit of interspersed sort of talking about these and how they're derived. But assume that these are for ideal gas at constant temperature or constant specific heat. All right, so if you combine these sets of equations, you can get new equations. You can see how this was working out. I mean, you could take so it's essentially take the exponent to each side and relate these R's and K's. And remember, this K is the ratio of specific heats, where K equals Cp over Cv. That's also, this slide is bad. Cp over Cv. Do you remember this? We talked a little bit about about the same kinds of equations that we use for a polytropic process. but now we're using them for an isentropic process. And it turns out that they are the same equations, just replacing k for n and k. But anyways, when you solve these isentropic relations, these are called the isentropic relations. Okay, so C is a specific ratio, Cp over Cv, and the equations, when they're solved, give these, which are called the isentropic relations. So T2 over T1 equals P2 over P1 to the k minus 1 over k. These are hugely important and very easy to use equations for the case where we have ideal gas, constant specific heat, and reversible process. You can use them for an isentropic throttling process, a compression and expansion process, the turbine, compressor, all sorts of things. If we assume isentropic and we assume constant specific heat's an ideal gas. That's a lot of assumptions, but we often make those kinds of assumptions when we're doing problems. So anyways, then you can get this set of relations which are actually really useful. Oh, this is using the PR. I'm not going to do this. But I am going to do. So you can look through this example. This example essentially tells you to calculate the final temperature using two different methods, and one is using the tables. You can use the PR and method, which I just didn't go over, or you can use the constant specific heat value. And in this case, you can see that you can calculate the temperature P2 using this relation here between those two states. Now, so the idea that if you look it up directly in the table, you can get the change in temperature as a function of changing specific heats, whereas the second one does not assume changing. So this one's T2 more accurate method is 339.7, and this one is T2 is 345.5. Okay, that's really not going to make a big difference, but certainly maybe one would be more accurate than the other. I don't really care. I kind of think constant specific heats is a fine assumption, and in combustion we do it all the time. So it's kind of neither here nor there. I think probably the method, which I haven't really told you about here with using the tables, is more accurate. But then most of the time we're going to assume that we have constant specific heats. Okay, so let's do a couple problems. I'm going to use the ideal gas model with constant specific heats to solve one of them, and the other one is actually a steam problem. So let's see, which one am I going to do first? I'm going to do the argon one first. So the first one we're going to do is it's argon in an isentropic process. So let me get my tablet out here and do some. Okay, so let's go like this. Okay, here we go. So example problem 1. We have argon in a piston cylinder assembly compressed isentropically from state 1 to state 2. State 1 and state 2 are kind of given here, and a K is given. When a problem says K equals something, that means they're assuming constant specific heats. Okay, so that's a constant K, constant specific heats, because K is equal to the ratio of specific heats. All right, so what we're going to do is we're going to solve this thing. So known. By the way, I want you to use these methods that we've been doing with these example problems over and over again for your exam. Okay, I want to see this procedure laid out. I know people think it's annoying and it's obvious and all this stuff, but just humor me. Put them in there, and you'll get all the points, and then I'll be happy. Okay, so known we have a piston cylinder. So we're back to pistons and cylinders again. Compression with an ideal gas. What we're going to find here is we're going to find the. Hopefully you can read that. Oh, you can read that, right? I hope my handwriting is just totally not degrading here. So find A, we're going to find T2, the second temperature, and B, we're going to find the work in kilojoules. Oh, that looks like little w. So little w in kilojoules per kilogram of argon. Okay, let's see. ideal gas, which is argon. So we don't need to know much about to solve this, but let's just say we're going to make some assumptions. And the assumptions will make this thing very easy to solve. Essentially, we have argon so it's a closed system, which we'll draw here in a minute. 2, we're going to assume that this is an isentropic process. It doesn't really say that, does it? Isentropically, of course it does. Okay. 3, so argon is an ideal gas. Ideal gas with K equals 1.67. It's interesting, argon. It reminds me of something a colleague at University of California, Berkeley is doing with argon in an engine. Remind me when I get to the engine cycles. Well, hopefully you can remind me, but I'll try to remind myself that when we get to the engine cycles, I'm going to discuss the idea of using argon as a working fluid in an engine, okay? Let me just make a mental note there, okay? Right now I'm not going to do that. I'm just going to get this problem done. 4, we're going to assume no delta KE and no delta PE. Okay, so we assume no kinetic or potential energy effects. And now let's make our diagram. So our diagram looks like the following, right? So we always have to make our diagram. You can be pretty much rest assured that there's going to be some kind of piston cylinder type deal on the exam, right? Because I do so many of them that it just would be silly for me not to put something like that on the exam. Might be a little trickier than what you might have been seeing, but it's going to be a piston cylinder, right? Some kind of piston cylinder going on. Excuse me. So this is the system, which we've labeled with our dotted line. We know you have argon in here. You have a piston. It's a compression process. So you're putting, well, we have work. They want us to find little w, so I'll put that in there. We're going to say it's insulated. Oops. So that's insulated, so I put insulation around the outside of it. Okay, so there's no Q. And then we also have, in this case, we can make a TS diagram, right? Because we know what everything is. So TS diagram, let's see. So P1 equals 300 and P2 equals 450. So 450 sort of, what is it? 450 sort of, what does it say? 450 is up here. And 300 is down here. So this is 450, this is 300 kPa, and then you have an isentropic process, which means that S2 equals S1 isentropic. Remember we said that? So this is straight down. So we're compressing to a higher pressure, so we're going like this. So this is state 1 and state 2. Okay, anything else? We don't know T2, so we don't know this one. But we do know this one is 37 degrees C. Okay, so we don't know T2. T2 is not known. That's what we're going to find. Oh, but it's so easy, right? So with those relations we just came up with, since we have constant specific heats with constant ideal gas, so this assumes here that we'll just say 3A, that it's constant specific heat, constant CV. Because they give us a K, we assume kind of automatically that it's constant CV. Okay, so now let's go. A is to find the temperature. We're going to use our new relations that we just came up with, which are called the isentropic equations. So we're going to use T2 over T1 is equal to P2 over P1 to the K minus 1 over K. I mean, how easy is that? So T2 then is equal to T1, which is 310K times 450 over 150, or is it 150? What's going on here? It's 300. I said 300. P1 is 300, and T2 is 450. Okay, so my solutions are different than my 300 or 450. Oh man. So I'm gonna have to check it, the solution here. Bear with me. So k minus 1 over k is 0.67 over 1.67. All right, let me get my handy phone out. I got a new phone, but the calculator is still just as bad as the other one. Let's see, calculator. Oh, does it let me do scientific? Oh, yes. Okay, good. So 450 divided by 300 equals to the where is it here? X to the y. Um, you can't see what I'm doing here, unfortunately. I'm sorry. 0.67 divided by 1.67 close equals times 310. I get 364. Oh yeah, so T2 2 equals 364.8. Okay, which is wrong compared to the solution I have, so it's good that we're doing this. So example 1 continued. We have B. Now we have to find the work. Now the work is based on the first law energy balance, right? Because remember, there's no work in the second law the second law balance. We're gonna have work. Um, well, let's just write the way they write it. So Q minus work is equal to U2 minus U1. Neglecting kinetic, so delta PE plus delta KE, which you assume goes to 0, and this goes to 0. So work is, so let's put it in terms of mass. Then we're going to say that work, oh, they work want or mass? Yeah, so they want work is equal to negative, so work is equal to minus U2 minus U1, which is equal to CV T2 minus T1, since we're assuming constant specific heats. And then, yeah, we could look up CV in the table, or we could use the relation that CV equals R over K minus 1. Now remember, this is not R bar, that's R. So it's 8.314 divided by the molecular weight of argon, which is 40, I think. Okay, anyway, so here we go. So work is equal to negative R K minus 1 times T2 minus T1. And this is 8.314 divided by 40 divided by 0.67. The whole thing divided by 0.67. That's 4. I mean, I'm sorry, what did we say? 364 minus minus the other temperature, 310. Okay, and if I just do this real quick on my calculator here, 8.314, oops, 8.314 divided by 40 equals divided by 0.67, which is equal to 0.310 times 54.8 is equal to negative 17, essentially negative 17 kilojoules per kilogram. Okay, so that's what you got. You get negative 17 kilojoules per kilogram, pretty much on the dot. Okay, which means it's work going in. So negative means work into control, into system. If it was positive work, it meant that we were getting work out by compressing, which of course you know we can't do. Okay, good. So let's do the other problem to finish us off here. So the other problem is steam undergoing an isentropic process. So steam is undergoing an isentropic compression. So it's in a piston cylinder. The same problem, it's just we're doing it with steam. From T1 120 to and some pressure to a final state, we don't know the final temperature and we don't know the work. So we're just going to essentially ditto what we did before. I wonder if I can do that. Hold on. Let's ditto this and copy it and see what happens. So let's just select all this stuff to make my life easier and just kind of pull this stuff out. Oops. Here, let's make sure I can copy it. All right. Oh, they're gonna let me copy it. I've not done this before, so this is why I'm a little bit tentative. Um, no, not gonna let me do it. All right, I'm gonna do it. Just do it again. All right. Let me be being lazy. I'm trying to be lazy, but okay. I don't let you guys be lazy, so why should I be lazy, right? So known, we have a piston. And this piston cylinder with steam undergoing an isentropic compression. Okay. We need to find, again, we're going to find T2, A, and B. We're going to find the work per kilogram, so little w. The assumptions, similar to last time, we're going to assume that we have, so we're not going to assume ideal gas, so we're going to assume that we have here closed system and 2 isentropic. Okay, and we're going to assume that it's S2 is equal to S1 and Q equals 0, right? And we're going to also neglect kinetic and potential energy. Okay, my diagram is going to look like identical to the last one. I mean, it's going to be an adiabatic piston cylinder arrangement where you have some work, and then you have a system, and here we're going to have water instead. It's insulated. This is our system. All right, so we've got that. All right, so now let's see. I see that people are asking about it, practice problems for the exam. I'm going to get those out. I promise I'll get them out right after lecture. I have a set that I can give out for people that you should have by tomorrow's lecture. So sorry about that. You should have some practice. Hopefully, been able to practice with the problems that we've got on the homework and with the problems that are in the book and stuff. But I'll send out some practice problems very soon. Okay, so I guess it's a little different than that we have the vapor dome in this case. Now, one thing is though, we might even be talking about superheated stuff. So let's see here. 120 and 1 bar. Okay, let's just think about it. 1 bar is where we live, right? 1 atmosphere. So if it's 120 degrees C, that must mean it's superheated, right? It's beyond 100 degrees C. We know 100 degrees C is the boiling point on Earth. So definitely we're in the superheat. So 0.1 or 0.2, I'm sorry, is down here. This is 1 bar. So we know it's superheated. We are lucky in that we do not have to calculate anything. We're superheated the whole time. That's a bonus. So pretty easy. So this is 120 here, 3C, and then this is some T2, which we don't know. But we know what pressure this is. We know this is 100 bar, and this is 1, okay? Okay, now let's do our assumption, our analysis. Sorry. So our analysis is going to be like this. So we know that S2 equals S1. So on table A4, we know superheat. We know that condition 1, so know that T1 equals 120 degrees C, and we have S1 equals 7.4668 kilojoules per kilogram. Okay, and we have to know what U is too. So U1 equals 2537.3 kilojoules per kilogram. So we need to know U because we have a closed system, right? H is not going to do us very good in this case. So then we need to sort of look it up. So if we look at A4 oh, in this case you have to extrapolate. I was just looking at the problem solution. Whatever. So if you go, so 120, you have to find a temperature at 100 bar. P2. I'd never make you extrapolate. That would be silly. But okay, so if you were to find these values in the table, you would look straight up in the 100 bar on the 100 bar saturated table, and you'd find that S2 is equal to the same thing. Ooh, S2 has to equal the same thing at 7.4 668 4668, and we know that U2 is equal to then we know essentially by looking at the table that T2 is equal to 821.3 degrees C. Okay, that'd be looking at a table. You define that by interpolating. And then we also know U2, little u2, is also equal to 3669.4 kilojoules per kilogram. All right, and then what we've got is essentially, so that's just sort of looking at the tables and interpolating. So we can obtain the T, so T2 is already found. We can find this in the table, so that's the first answer. And then, we can find the work. So work is, okay. So we find work here, a little work is equal to U2 minus U1, because if we do the first law, we have Q minus W equals delta U plus delta KE plus delta PE, where these go to 0 because we said those are 0, and we said this was 0. So negative work equals U2 minus U1. Right, remember that? Okay, this is what we did in the last problem, and so essentially we don't need to know anything about mass because we're calculating it as a function of mass, normalized per mass, and we just 3669.4 minus 2537.3, and this is equal to, I don't really have the answer here, do I? It's negative this. So work is equal to 3669.4 minus 2537.3, and is equal to negative 1132 kilojoules per kilogram of steam. Okay, again, it's work in. It's always nice to indicate that, whether you have work in or out, interpreting your result. I like interpreting results, so if you say this is negative, it must mean that the work is leaving the system. Or I'm sorry, work is going into the system. Whereas Q is positive, you'd say that's heat going into the system. Okay? All right, I think that does it. So these are just a couple examples of isentropic processes. We can make them harder than this, but this was just sort of a real easy way to get you accustomed to using these isentropic process rules. So as I said, if we're steam, use the tables. For ideal gas, when we're given a K and a constant specific heat, you assume that you use that you just essentially use these isentropic relations. Okay. All right. So that with that does it. So I'm going to get going and giving you guys some example problems to work with. And one bonus: there is no homework assigned for Friday. I forgot to tell you that. No homework. Just focus on the exam. Then you don't have anything to do on Thursday night for this class. I will assign homework again on Friday to be due on Monday. Okay, so no homework. Just worry about the exam tomorrow, and good luck. Okay, and please let me know again if you have any questions or concerns, and I'll help you answer those. Okay, bye now.